Welcome everyone to the next video of Signals and Systems tutorial video sequence. And here comes the next question. Determine the impulse response of the following system using Fourier transform method. And you are given a difference equation connecting y of n and x of n. Okay, so in here you have given a discrete time signal. That means the Fourier transform they are intending is nothing but discrete time Fourier transform, DTFT. Okay, so in such questions we don't have any other option but to take Fourier transform on both sides of this difference equation. So while taking Fourier transform or DTFT on both sides of the difference equation, we will get what is the first term is y of n. So the Fourier transform of y is y of e raised to j omega minus 1 by 6 into next is y of n minus 1. Its Fourier transform will be, listen, it is a time shifted signal, so we have to multiply the frequency domain by e raised to minus j omega, right? So e raised to minus j omega into y of e raised to j omega minus 1 by 6 into next term contains the y of n minus 2. So it is having a Fourier transform e raised to minus j omega 2 into y of e raised to j omega. Okay, because it is a time shifting again. Okay, equal to, in the RHS we can see x of n. So its transform will be x of e raised to j omega. Okay, now similar procedure we have followed in many questions in the previous part of the videos. You take y of e raised to j omega outside, so 1 minus 1 by 6 e raised to minus j omega minus 1 by 6 e raised to minus j2 omega will be equal to x of e raised to j omega. Listen, the question is to find the impulse response. What is the impulse response? Impulse response is nothing but you can see the frequency response h of e raised j omega. If h of e raised j omega is the frequency response, then the inverse transform, inverse DTFT will give you h of n, which is nothing but the impulse response. And the question is, how will you get h of e raised to j omega? It is nothing but y of e raised to j omega divided by x of e raised to j omega. Okay, so that's what we are going to get from this equation. Okay, so we can proceed with finding y of e raised to j omega by x of e raised to j omega, because that will give you the frequency response h of e raised to j omega, and that is equal to 1 divided by 1 minus 1 by 6 e raised to minus j omega minus 1 by 6 e raised to minus j2 omega. Now that we got the frequency response, our aim is to find the inverse transform. But as such, we cannot find out the inverse transform because you can see the denominator is not in a factorized form; it is in a polynomial form. So we have to convert it in a factorized form. So this is equal to 1 by for factorization, you have to think of two numbers whose sum is minus 1 by 6 and the product is also minus 1 by 6. Okay, you have to get two numbers whose sum is minus 1 by 6, product is also minus 1 by 6, and I think minus 1 by 2 and plus 1 by 3 will do it, right? Minus 1 by 2 plus 1 by 3 is nothing but 1 by 3 minus 1 by 2 is minus 1 by 6, correct? And 1 by 2 into minus 1 by 2 into plus 1 by 3 will give you again minus 1 by 6. So these two are our numbers, minus 1 by 2 and plus 1 by 3. So you write like this: 1 minus 1 by 2 z inverse, that is one factor, into 1 plus, it is plus 1 by 3, so for 1 plus 1 by 3 z inverse as a second factor. So we have factorized it. Now it is very simple. We have to take the partial fraction expansion, a by 1 minus half z inverse plus b by 1 plus 1 by 3 z inverse. Okay, and now how to find out the values of a and b? You take the term containing a. Look at the denominator. It is 1 minus half z inverse, right? So to find a, you multiply this 1 minus half z inverse with the total partial fraction, right? Total fraction. That will give you only 1 by 1 plus 1 by 3 z inverse alone. And now put z inverse is equal to some value which makes this denominator 0. So what is that value of z inverse? You have to look at, a equal to, first you multiply with 1 minus half z inverse with the main fraction. So you will get 1 minus 1 plus 1 by 3 z inverse. But you have to evaluate it for z inverse equal to, select z inverse for such a value which makes this denominator as 0. That is, I think, z inverse equal to 2, right? Z inverse, if you put z inverse equal to 2 here, this becomes 1 minus 1, that is 0. Okay, so evaluate this at z inverse equal to 2. Okay, that will give you 1 by 1 plus 1 by 3 into z inverse is 1 plus 1 by 3 into 2. So 1 plus 2 by 3. That will give you 1 by 5 by 3, that is 3 by 5. Okay, in a similar fashion, we can find out b as b is equal to, you take this factor, multiply with this thing. So this factor goes off. The remaining is 1 by 1 minus half z inverse. And put z inverse equal to what? Put z inverse equal to minus 3. Z inverse equal to minus 3 will make this fraction 0. This denominator 0. So b equal to 1 by 1 minus half z inverse, but put z inverse is equal to minus 3. So that will give you 1 by 1 plus 3 by 2, which is equal to 2 by 5. Okay, so our a equal to 3 by 5 and b equal to 2 by 5. So we can resubstitute these values. Therefore, h of e raised to j omega is equal to 1, a by 1 minus half z inverse. A is equal to 3 by 5. So 3 by 5 into 1 by 1 minus half z inverse plus 2 by, b. What is b? B is 2 by 5. 2 by 5 into 1 by 1 plus 1 by 3 z inverse. Okay, so we got the partial fraction expansion. Therefore, h of n is equal to, h of n is nothing but the inverse DTFT. Inverse DTFT of h of e raised to j omega, which will give you 3 by 5 into, what is the inverse DTFT of this function? This is a standard result. Okay, this is standard result. You know, it is half raised to n u of n. Okay, because any transform of the form 1 by 1 minus a raised to n z inverse, its transform will be a raised to n u of n. Okay, so that's what I have done here. So this is 3 by 5 half raised to n u of n plus, plus similarly 2 by 5 into, what is the inverse transform of 1 plus 1 by 3 z inverse? It is 1 plus. So we have to put minus 1 by 3 to the power n u of n. Okay, so this is the impulse response and final answer to the question. Okay, we shall try the next problem. Plot the pole zero diagram and assess the stability of the following system. And you're given a difference equation y of n equal to y of n minus 1 minus half y of n minus 2 plus x of n plus x of n minus 1. So the question is to plot the pole zero diagram of a system and then assess the stability. So to assess a system or to plot the pole zero diagram, what we need is the transfer function of the system, because transfer function is one thing that specifies a system. We know majority of the parameters of a system can be detected from either its transfer function or its time domain impulse response. Okay, so we have to get the transfer function of this system from the clue they have given us, a difference equation. Okay, so how to find out the transfer function from this difference equation we have seen many times, and even in the just previous video we have seen it. Okay, so In order to find the transform function in Paul 0 diagram, Z transform will be the best. Okay, Z transform will be the best. So take Z transform on both sides. That implies y of z will be equal to z to the power minus 1 into y of z minus 0.5 into z to the power minus 2 into y of z plus x of z plus z to the power minus 1 x of z. Okay, I think it will be clear because what I have used here is just a time shifting property of Z transform, because time shifting property says that if x of n and x of z are Z transform pairs, then x of n minus 1 will be having a Z transform of z raised to minus 1 x of z. Okay, 1 unit shift means 1 unit shift in the frequency domain. Okay, exponential domain. Okay, so now what we have to do is you have to arrange all the y of z terms in one side. So y of z into 1 minus z inverse plus 0.5 z inverse 2 is equal to x of z into 1 plus z inverse. Okay, now transfer function is given by y of z by x of z, output transform by input transform. That is your transfer function h of z is equal to, you can write 1 plus z inverse divided by 1 minus z inverse plus 0.5 z inverse 2. Again, I'm inviting your attention towards the question. The question does not ask you to find out any impulse response or something, but just to plot the pole zero diagram. And from that we can assess the stability. So to plot the pole zero diagram, I think this z inverse form is not at all desirable, so we have to make it to z form, z square or 0 to 1 form. So for that I am taking z inverse as 1 by z divided by 1 minus 1 by z plus 0.5 by z square. Now taking the LCM, we can write h of z is equal to z plus 1 by z, that is the LCM of the numerator, divided by z square minus z plus 0.5 whole divided by z square, that's the LCM of the denominator, and we can cancel z here, which will ultimately give you this particular transfer function, which is given by z plus 1 divided by z square minus z plus 0.5. So this is another representation of the transfer function. Apart from this representation, this is also correct. Okay, this is also correct. And now it is very simple to deduce the pole zero plot from this transfer function. Actually, what is zeros? Zeros means those values of z which makes the numerator to 0. So z plus 1 equal to 0 means z equal to minus 1. Okay, z equal to minus 1 is the 1 0. Oh yes. I have this is z here, right? Okay, 1 z and only 1 z cancel, so a z will be here. Okay, so z into z plus 1, that's the correct one. Okay, z into z plus 1, sorry for that. So okay, so 0 means whatever particular values of z that makes this numerator to equal to 0, that are the zeros. So I can write zeros of the transfer function are z into z plus 1 equal to 0. That implies either z equal to 0 or z equal to minus 1. So both of these are actually the zeros of this transfer function. Okay, so we got zeros. Now what are poles? You have to find out poles also, right? How can you find out poles? You know, poles are those values of z that gives the denominator to 0. So we have to equate denominator z square, right? Z square minus z plus 0.5 equal to 0. How will you find out the values? You can use any method. You'll be familiar with the method b square minus 4ac, right? Z equal to minus b plus or minus root of b square minus 4ac by 2a, where a is the coefficient of z square plus b is the coefficient of z and c is the constant. Okay, so that implies z is equal to Minus b is actually minus of minus 1 plus 1 plus or minus root of b square is minus 1 square. So 1 minus 4 into a is 1 and c is 0.5. So 4 into 1 into 0.5 whole divided by 2a, 2 into 1. Okay, that will give you z equal to 1 plus or minus root of 1 minus 4 into half is 1 minus 2, right? 1 minus 2 is minus 1. So root of minus 1 is j. Okay, j whole divided by 2. So I can write it as zeros are at z equal to half plus or minus half j. Okay, half plus or minus half. That means z equal to one pole is half plus j by 2 and other is half minus j by 2. So you have to make an important note here that if at all a pole is a complex pole, you can see a j term here. This is a complex pole. Always its conjugate will be there. For this system, if at all a complex pole comes, its conjugate pole also will be a pole, another pole. That's always true for all systems. For the case of complex poles, zeros also. If at all there was any complex zeros, its conjugate also will be there. Okay, so we have got the zeros and poles. Now they have asked us to plot the poles and zeros. We can do that very simply. So I have drawn the z-plane for you to plot the pole zero plot of the system, and we have got the poles as half plus or minus j half, and zeros as z equal to 0 and z equal to minus 1. Okay, first let me plot the zeros. Usually zeros are plotted by marking a 0 wherever they are on the z-plane. So z equal to 0, is nothing but the origin. So this is a 0. Okay, this is a 0. And z equal to minus 1 is another 0. Z is equal to minus 1 means it is here. So here also we can see a 0. Alright, now poles. What about the poles? First pole is half plus half j. Right, half plus half j means half in the x-axis and half in the y-axis. So they come somewhere here. Okay, poles are usually represented by a cross mark or into mark. Okay, so this is half plus half j, half plus half j pole. Okay, right. Now one more pole is there, which is half minus half j, which is just the complex conjugate. Complex conjugate means it is having the same magnitude but different phase. So this is half minus half j. Okay, half in this axis and minus half means fourth quadrant. So this, right? So this is the pole zero plot of this system. And finally in the question they have asked us to find out one more thing to assess the stability. To assess the stability of the system. How will you assess the stability of this system from the pole zero plot? It's very simple. If at all the poles, right, all poles are inside the unit circle, then the system is stable. Right, all the poles are inside the unit circle, then the system is stable. There are totally 2 poles, and where are they, inside or outside the unit circle? Where is the unit circle? This is the unit circle because it is one radius 1 apart, right? This circle is having 1 radius. That's why we call it a unit circle, and both the poles are inside this unit circle. That means the system is stable. So the next question is, find the DTFT of the signal if Z transform is given by x of z equal to z by z minus 0.2 into z plus 0.9. if you are amazed by this question and don't know how to do this, this is a very good news, because this question is very simple. I think this is the simplest of all the questions in this section, because all you need to know is the relation between DTFT and Z transform. And this relation was discussed in just the previous video. I think it is part 22 of our lecture sequence, which says DTFT is, I can quote it again, DTFT is nothing but Z transform evaluated along the unit circle. Okay, this question is just a one-step solution question, and all you have to know is the theory and the concept. DTFT is Z transform evaluated along the unit circle in Z plane. You might be remembering in the previous video I've taken the Z plane, and then drawn a unit circle. Unit circle is nothing but Z equal to R e raised to minus j omega, where R is equal to 1, modulus is equal to 1, right? So that defines the unit circle. Then we have taken the definition for Z transform. X of Z is equal to sigma n equal to minus infinity to plus infinity, x of n Z raised to minus n, but Z equal to R e raised to minus j omega. But at the unit circle, mod Z equal to 1, that means R equal to 1, so Z is equal to e raised to minus j omega, right? So putting this, that implies x of Z equal to e raised to minus j omega is equal to sigma n equal to minus infinity x of n into Z is e raised to minus j omega, so e raised to plus j omega, it is e raised to plus j omega. Okay, e raised to plus j omega. So Z raised to minus n gives you e raised to minus j omega n. Okay, and to our astonishment, this expression, we started with Z transform, but this expression is nothing but DTFT. Okay, so that's why we concluded that DTFT is the Z transform itself evaluated along the unit circle in Z plane. Okay, so from the question, now you just listen to the question. To find DTFT from this Z transform, what you need to do is just put Z equal to e raised to j omega. Just put Z equal to e raised to j omega. So given x of Z equal to whatever, Z divided by Z minus 0.2 into Z plus 0.9, put Z equal to e raised to j omega, because DTFT is nothing but Z transform evaluated along the unit circle 1 into e raised to j omega. Okay, so therefore the DTFT x of e raised to j omega is equal to Z is e raised to j omega, so e raised to j omega divided by e raised to j omega minus 0.2 into e raised to j omega plus 0.9, and that concludes the answer. Let's move forward to the next question. A discrete time LTI system is characterized by the impulse response h of n equal to half raised to n of n. Use Fourier transform to determine the response of the system to the input x of n equal to 3/4 to the power n u of n. So you're given impulse response and the input, and the system is an LTI system. So the question is to find the output. Okay, response of the system means it is output of the system. Okay, so you have to listen that this is actually a very much repeated question, right? You are given an LTI system, you are given its impulse response and one of the input, find the output. Okay, so we have started from the section 1 itself. Section 1 or section A, we have found out the output using convolution integral or convolution sum, and now we are using it, or we are finding the output in a different approach, which is nothing but the property called convolution property, because if it are in time domain, y of n is equal to x of n convolution h of n. In frequency domain, be it in Fourier transform or be it in Z transform or be it in Laplace transform, whatever be the transform is, y of j omega, omega will be equal to, just multiply x of omega into h of omega. Okay, see how convenient this property is, because in time domain convolution is a bit hectic, right? If at all the signal length or signal amplitudes are very high, or their transitions are very frequent, then finding the time domain convolution is a bit hectic. But in this frequency domain, it's just multiplication, very simple. Okay, so this is a very powerful property we have, and using that we can find out the output to the system, to this LTI system. So we know h of n is equal to half raised to n u of n, and the question is given that we have to find out the output using Fourier transform approach. Okay, so we can either take Z transform, but in the question it is specified that Fourier transform is to be taken. Okay, so we can move forward with Fourier transform. Therefore, what is the Fourier transform of this signal half raised to n u of n? It is a standard result, 1 by 1 minus half e raised to minus j omega. Okay, this is the Fourier transform of h of n, which is given by or denoted by h of omega. Now they have given us input signal also, x of n equal to 3 by 4 raised to n u of n. X of n equal to 3 by 4 raised to n u of n. And now what is the Fourier transform of this signal, input signal x of omega? Again, this is the same similar kind of signal, right? So we can use the same property or same standard result, which is 1 by 1 minus 3 by 4 e raised to minus j omega. Okay, so we have in our hand the Fourier transform of the impulse response and the Fourier transform of the input. Therefore, using this convolution property, I can write, therefore, the transform of the output y of omega is nothing but h of omega into x of omega, which is equal to 1 by 1 minus half e raised to minus j omega into 1 minus 3 by 4 e raised to minus j omega. Okay, now our aim is to find out the inverse transform, so that the time domain output y of n is obtained. But to obtain the inverse transform from this thing, this is in a factorized form, so we can definitely find out the partial fraction expansion. Okay, a by 1 minus half e raised to minus j omega plus b by 1 minus 3 by 4 e raised to minus j omega. Okay, and we have seen how to find out the partial fractions a and b in this video itself. Okay, therefore I'm moving a bit faster. So a equal to 1 by 1 minus 3 by 4 e raised to minus j omega evaluated at e raised to minus j omega equal to 2. Okay, so that is 1 by 1 minus 3 by 2, and that will give you minus 2. Okay, so a equal to minus 2. Similarly, what is b? B is equal to 1 by 1 minus half e raised to minus j omega evaluated at e raised to minus j omega equal to 4 by 3, and that will give you 1 by 1 minus 1 by 2 into 4 by 3, which is 1 minus 2 by 3, right? Yeah, so that is 3. Okay, so b equal to 3. Now I can make use of these results and rewrite our original transform function as transform as y of omega equal to 1 by 1 minus half e raised to minus j omega into 1 minus 3 by 4 e raised to minus j omega equal to a by 1 minus half e raised to minus j omega. For a, we have gotten as minus 2 into 1 by 1 minus half e raised to minus j omega plus b is 3 into 1 by 1 minus 3 by 4 e raised to minus j omega. Okay, now it is very simple to find out y of n. Just take the inverse transform, minus 2 into this is of our standard form, this is also of the standard form, so we can readily find out the inverse transform as 1 minus 2 into half raised to n u of n plus 3 into 3 by 4 to the power n u of n. So this is the response of the system. Okay, over to the next question. Determine the Z transform and plot the ROC of the signal starting from the definition of Z transform. X of n equal to a raised to n u of n minus b raised to n u of minus n minus 1. So we have to find the Z transform of this signal. This is a combination of two particular signals, and we have to do the Z transform from the definition. They have clearly mentioned from the definition. Okay, so we will start from the scratch. Let me take them as two terms. X of n is equal to a raised to n u of n plus minus b raised to n u of minus n minus 1 as x1 of n plus x2 of n. Obviously, x1 of n is equal to a raised to n u of n, and x2 of n will be equal to minus b raised to n u of minus n minus 1. So on inspection itself, one thing is very clear, that a raised to n u of n is a right-sided signal. Okay, and minus b raised to n u of minus n minus 1 is a left-sided signal. Okay, you have to save this in mind. Okay, now we'll start to find for a transform x of n, x1 of n, which is a raised to n u of n. Okay, therefore x of z is equal to, we know the definition of Z transform. What is the definition of Z transform? X of z is equal to sigma over n equal to minus infinity to plus infinity, the signal into z raised to minus n. Alright, so in the case of x1 of n equal to a raised to n u of n, the signal, the sigma is need not from minus infinity to plus infinity, but it can only be from 0 to infinity, because in the signal there is a u of n being multiplied with a raised to n, so it truncates all the values in the negative n side. So only n equal to 0 to infinity, positive n samples only exists. So I can take the summation from n equal to 0 to infinity instead of summating from minus infinity to infinity. So x of n is a raised to n into z raised to minus n is remaining, into a raised to n into z raised to minus n. Okay, so this is equal to, we don't have any other option but expanding the sigma, that will give you n equal to 0. When you substitute n equal to 0, it will be a into z, n equal to 0 means it is 1, right? N equal to 0 means it is 1. A raised to 0 into z raised to 0 is 1, plus n equal to 1 means it is a z inverse raised to 1, plus n equal to 2 means a z inverse to the power 2 plus etc. and goes to infinity. This is an infinite sum, and if you observe closely, this is a GP also. So this is an infinite GP whose sum is given by it is a by 1 minus r. Okay, provided mod r is less than 1, the common ratio should be less than 1, right? So this is equal to, I can apply this equation. A means first term is 1. So 1 by 1 minus, what is the common ratio? Common ratio is A into Z inverse, right? Because you multiply A into Z inverse with this term to obtain this term. Okay, again you multiply A Z inverse with this term to get A Z inverse square. Okay, so obviously A Z inverse is the common ratio. So this is the Z transform to the first signal a raised to n u of n, but provided we have one condition here, mod r is less than 1. We can take this equation only if mod r is less than 1, so we have to assume that. So mod of r is a z inverse, that is less than 1, or in other words, this implies we can write mod of a by z is less than 1, or mod of a less than mod of z, or inverting, that implies mod z greater than mod a. Okay, so this is the Z transform 1 by 1 minus a z inverse and ROC of the Z transform of the first signal, first term. Okay, so this is obvious, we have studied this, right? We have studied this as a standard result. If we have a raised to n u of n signal, its Z transform is 1 by 1 minus a z inverse, or you can write it again as z by z minus a. Both are right. Okay, so and the ROC is mod Z greater than mod A, and I have already told you this is a right side signal, so its ROC will be of the form mod Z greater than mod A. Mod Z greater than mod A means if you choose a circle with radius A, which is the pole, then mod Z greater than mod A means all the points outer to the pole, outer to the circle whose radius is the pole A. Okay, so this is the ROC. Okay, so that was the first term. The second term is x2 of n, right? x2 of n is equal to minus b raised to n u of minus n minus 1. Okay, let us attempt to find the z transform of this signal. So x of z is equal to, or I can give this x1 of z and this as x2 of z. x2 of z is equal to sigma n equal to, what should be the summation here? From minus infinity to plus infinity? No need, because b raised to n or minus b raised to n is a two-sided signal. Okay, if okay, I can draw this as, this is b raised to n. And what is u of minus n minus 1? U of n is this signal, right? U of n minus 1 means we are shifting the signal 1 unit to the right. Okay, so the signal starts only at n equal to 1, 2, 3. So this is n. Okay, this is u of n minus 1. And what is u of minus n minus 1? You flip the signal around the y-axis. So all these samples go to the, symmetrically go to the other side of the y-axis. So this is a signal. Okay, so this is u of minus n minus 1, and you are multiplying this signal with this signal, means all these components are gone, even including n equal to 0 component. So the resulting signal is only having values from minus 1 to minus infinity. Okay, so the sigma will be from minus 1 to minus infinity. You have to be very careful about that. Okay, the sigma is n equal to minus 1 to minus infinity. The signal is minus b raised to n. Now you don't have to put u of minus n minus 1 there, because its effect has been shown in the truncation of the signal in the positive n axis. Okay, so minus b raised to n into 0 raised to minus n. So I can write it as, maybe I can erase this thing to save some space. Okay, so I think this is, I can take the minus negative sign outside the sigma, n equal to minus 1 to minus infinity, and b raised to n, 0 raised to minus 1, I can write it as b into z inverse the whole raised to n. Okay, now you do one thing, you expand the summation. So put n equal to minus 1. First value of n is minus 1, not 0. There is no 0 involved here. Minus 1 to minus infinity. So n equal to minus 1 means it becomes b z inverse to the power minus 1. Okay, the next value of n is minus 2. So b z inverse to the power minus 2 plus b z inverse to the power minus 3, and goes to minus infinity or infinite times. Okay, infinite terms. So again, this is a GP, infinite GP. You can rely on the same equation, a by 1 minus r, given mod r is less than 1. So what you will get is, this is equal to minus of, first term is b z inverse the whole inverse divided by 1 minus, what is r? R is again b z inverse the whole inverse. Okay, if you multiply bz inverse with bz inverse only, you get bz inverse raised to minus 2, right? If you're confused, this is the first term. Okay, this is the very first term I have written here. Okay, and what is the second term? Second term is bz inverse the whole raised to minus 2. If you divide second term divided by first term, what you will get is bz inverse whole raised to minus 2 minus 1, that is bz inverse to the power minus 1, and that is mod r, right? So that is I have written here as mod r. Okay, So we have got it as minus bz inverse the whole inverse by 1 minus bz inverse the whole inverse. We can do a little simplification. So bz inverse the whole inverse is 1 by bz inverse whole divided by 1 minus 1 by bz inverse. Okay, we can take the LCM. This is equal to minus 1 by bz inverse divided by bz inverse minus 1 by bz inverse. Readily we can cancel these things. So this will give us mod x2 of z is equal to, here it is a minus, right? I can take this minus to multiply this term, which will give me the answer as 1 by 1 minus bz inverse. So this is the z transform of the second term, which is nothing but minus b raised to n of minus n minus 1. See, here minus comes, the transform has no negative, it is positive. Okay, now one more thing is pending. What is that? It is the ROC, nothing but ROC. And what is ROC? How will you find out the ROC? ROC is found out from the assumption we have taken here while applying a by 1 minus r, this summation of the GP, which is nothing but mod r is less than 1. Mod r is nothing but bz inverse the whole inverse. So I can find ROC as ROC is mod r less than 1, or bz inverse the whole inverse is less than 1. Okay, or we can write, or I can write b by z the whole inverse is less than 1. Okay, or that means what is b by z the whole inverse? It is it's actually z by b, right? Z by b. Okay, so mod z by b less than 1, that will give you directly mod z less than mod b. Okay, so the ROC of this term alone is mod z less than mod b. Okay, and how will you plot the ROC? Obviously, in the question, from the question itself, this signal is a left-sided signal, right? We have drawn it somewhere here. Okay, so this left-sided signal will be having a z transform or ROC of the form mod z less than mod b, which is nothing but I can draw here, which is nothing but, if I'm drawing a circle with the pole b as the radius, then mod z less than mod b means all of the z plane which is less or inner to this circle, whose radius is the pole. Okay, so we have so from the question, what is the question? The question asked us to determine the z transform and plot the ROC of the signal. Okay, so the total ROC of the signal x of z is equal to x1 of z plus x2 of z, which is 1 by 1 minus a z inverse plus 1 by 1 minus b z inverse. So this is the total z transform. And what is the total ROC? ROC is the intersection of the individual ROCs. You can see the ROC of this term was mod z greater than mod a, and ROC of this term was mod z less than mod b. Okay, so I can draw in the z plane where we can see the intersection occurs. So I have drawn the z plane and the pole 0 plot. You can find the pole a, and I have drawn a circle with radius a. Also the pole b here with a circle with the radius pole b here. And I have assumed that mod a is less than mod b. You can see why I have assumed mod a less than mod b later. Okay, so if at all the first term will be having mod z greater than mod a, right? So the ROC will be outer to the pole or outer to the circle having pole A as the radius. So this is the ROC corresponding to the first term, mod z greater than mod A. What I am drawing is the ROC mod z greater than mod A. Clearly the first term was a right side causal signal, so its ROC is of the form outer to the outer circle. Okay, and now what will be the ROC for this term, mod Z less than mod B? Mod Z less than mod B means it will be inner to the circle, right? Inner to the circle, the whole of Z plane, which is inner to the circle with the pole B as the radius. That means this shaded region. Okay. Okay, so the red sided and the green sided regions are the individual ROC of the particular terms. Now, what is the ROC of the total Z transform? It will be the intersection. And what is the intersection? Intersection is nothing but this area. Which area? The area between A and B. So I can write or I can shade this portion, right? This is the portion where we can see the both of these individual ROCs intersect. Okay, individual ROCs intersects. So this is the ROC of the total signal, total Z transform, and we can express ROC as mod, right? Mod A less than mod Z less than mod B. This is the ROC of the total signal. Okay, and we have to pause and ponder one more thing. What happens if my assumption is different, mod B greater than mod A? What will happen? What happens is, I can explain. I can again draw two circles with the mod A. Okay, this is the assumption should be mod A greater than mod B. I'm reversing the assumption. Previously we have assumed mod A less than mod B and drawn and obtained the ROC as this thing. Okay, now I'm going to reverse it. Mod A greater than mod B. So mod A greater than mod B means this will be the circle, right? Okay, so what happens to mod Z greater than mod A? Mod Z greater than mod A means this will be the ROC for the first term, the right sided signal term. Okay, and what means what happens to the second term, mod Z less than mod B? It will be this term. So this is these are the individual ROC plot of the signal if we have assumed like this. And what is the problem here? The problem is there is no intersection. There is no intersection. So Z transform will not exist if our assumption was like this, mod A greater than mod B. So Z transform exists. That means an intersection of ROC exists only when mod A less than mod B. Okay, so this is the answer to this question. Okay, we will quickly go through one more problem. Establish the correspondence between S plane and Z plane. Question is very simple, but it is very thick in concept. They're asking about the relations or similarities between or correspondence between S plane and Z plane. You know, the answer should include the following points. First point is S plane consists of analog frequencies, and whereas Z plane, this is analog complex frequencies. Real frequencies is for Fourier transforms. So analog complex frequencies, and Z plane corresponding to complex digital frequencies. Okay, the first and important point. And next I can say we can relate Z plane and S plane, or any point on Z plane and S plane, like Z equal to e raised to S into Ts, where Ts is the sampling interval. Ts is the sampling interval. Okay, the next points are very important. I can say all points on the left half of S plane, all points on the left half of S plane can be mapped to, all points on the left half of this plane can be mapped to the interior of the unit circle in Z plane. Interior of unit circle in Z plane. Okay, in Z plane we have a hero there, unit circle. That was very important there. Okay, so all points on the left half of this plane corresponds to the interior of the unit circle in Z plane. I will show this how. Okay, listen. So the yellow shaded portion means this is the left half of the S-plane. This is S-plane, this is Z-plane. So this shaded portion is the left half of this plane. And now listen very carefully. The point says that all the points on the left half of the S-plane corresponds to interior of unit circle in the Z-plane. You know, this is the unit circle. So the interior of this unit circle means these points, right? These points. Okay, so the mapping is like this. Okay, so all points on the left half of this plane is mapped to the interior of the unit circle. The next point is all points on the right half of the S-plane, all points on the right half of the S-plane maps to, you can imagine, maps to the exterior of the unit circle in the Z-plane. Exterior of the unit circle in Z-plane. I can illustrate this with a diagram. Okay, I have plotted the S-plane and Z-plane for the second time. Now the shaded portion means the right half of the S-plane. This is the right half of the S-plane. And how it maps is, it maps to the exterior of the unit circle in the Z-plane. That means this area. Exterior to the unit circle. The circle is unit circle because its radius is 1, assume. So exterior to the unit circle means it extends up to infinity. But all these regions are exterior to the unit circle. Okay, so the mapping is like this. Right half of the S-plane to the exterior of the unit circle. Okay. And finally, all points on the j omega axis on the S-plane. All the points on the j omega axis of S-plane gets mapped into the unit circle, on the unit circle, or on the unit circle in Z-plane. This is clear, right? All the points on the j omega axis, exactly on the j omega axis, will be mapped to the points on the unit circle in the Z-plane. Okay, so this is the S-plane and this is the j omega axis. Now this is the Z-plane and this is the unit circle on the Z-plane. So this point says that all points on the j omega axis, strictly on the j omega axis, will be mapped strictly onto the unit circle. Okay, previous point was all the points on the right half of S-plane goes to the exterior of the unit circle. All units of the left half of S-plane goes to the interior of the circle, and the final point maps all the points on the j omega axis goes on to the unit circle. This is the mapping. Okay, so this is the relation between correspondence between S-plane and Z-plane.